Okay, page 8, guys. We started talking about U-substitution and how for problems that we can't manage using power rule or with the trig rule that we have, anything that's more complicated, then our next option is U-substitution. The whole point of U-substitution is to allow for some derivative expression that is in a messy form for us to be able to take put that chain rule back into the proper form before the derivative took place. So we did that with previous examples, but we also talked about how some problems, they are kind of mass like U-substitution, but they're not really, there's no need for U-substitution. And the reason why is because there is nothing too complicated for us to just rely on power rules. So just be aware that if you see parentheses, it doesn't always mean that it's going to be U-substitution, especially if we can think of it as a problem that we were able to handle from the previous quiz, right? Just being able to separate into individual fractions, clean them up, individualize each term, and apply power rule there. We started talking about this change of variable idea where we still went through U-substitution, but we hit a roadblock when we realized that the x's did not go away on its own after we made the U-substitution. So we had to go through another set of substitution to get that x in terms of u. We can't just ignore it. We can't pull it to the front and just think of that x as a standalone coefficient. It's a variable. That variable is not allowing us to move forward until we've dealt with it. So the workaround is to look at the assigned equation that we built with U-substitution. If we rearrange that equation, we can solve for x. If we let x equals u minus 3, then we're able to now move forward because we couldn't distribute here, but now we can distribute here because this is radical for just one term. Distribute that through. Once we distribute that through, then each term is ready for power rule. Then we apply power rule for each term. And then when we get our answer, our antiderivative, keep in mind that u is only a temporary variable. We want to make the u go back to the original variable of this term. In this case, the original variable is x. Okay, so let's take a look at example 8. All right. There's a similar feel to it from example 7, but let's just go through our steps. First step, can we expand? Can we distribute this way? Can we distribute our way through this problem? No. Okay, so same with example 7, right? We're stuck. We can't expand. Our first option is not feasible. So our next option is U-substitution. Yep, good. So let's get the parentheses to show up. We know that we're making U-substitution as a potential option here. So let's get the parentheses to show up. 2 minus x raised to the 1/2. Okay, what could be our u value? We always target what's inside the parentheses. But what issue do we expect to see after we make our substitution? Yeah, this x squared won't cancel out. Okay, so we know that we're going to go down the same path that we did with example 7. We know we got to take care of that x. That x is not going to go away on its own. Okay, so let's go through our steps. All right, so u equals 2 minus x. Solve for dx. Okay, so when we make our substitutions, our goal is to just replace what we've underlined, but everything else we're going to leave in the problem unchanged. I'm sorry? Right, so u equals 2 minus x. We want to find the derivative. So du dx equals, what's the derivative of 2? 0, right? What's the derivative of negative x? -1, right? Yeah, so that's where that -1 came from, right? And then I cross multiplied here. Negative dx equals du. I guess I skipped a step here. After I cross multiplied, I solved for dx, and I just moved that -1 over. Dx equals -1 du. All right, any questions so far? Okay, so let's make our substitutions, right? We want to replace what we have underlined initially. Everything else we want to keep. Okay, so we know we can't go further. We can't just jump into power rule and say, okay, power rule here, and then plus c, right? That multiplication is preventing us from just applying power rule like we normally would. So we know the x squared is, take some additional step here. We want to get everything in terms of u before we do power rule, or before we look at integral rules. So what's our workaround for this variable that's sticking out? Good. We have that u equals 2 minus x. How can we rearrange this equation? X equals what? Okay, x equals 2 minus u. So this piece is going to replace this x. Question so far? All right, so this is going to take a little bit more effort here, but at least we have a path towards getting this cleaned up, right? Before, we couldn't even do any sort of cleanup, but this still requires cleanup, but at least we can get there. So what's needed here before I can do power rule? Okay, yeah, I want to distribute, but before I distribute, I need to do what? Yeah, I need to expand this out, right? I can't distribute this u to 1/2 through, but that power is manageable. I can FOIL this out and distribute this through. I'll rewrite it in this way here. This feels more clean to me. I still have to do the same thing, but here I'm going to pull the -1 and the 1/2 out in front, and I'm just going to, I don't know. To me, this feels cleaner because then I can FOIL this out, and I see this term in front. After I FOIL this out, then I can distribute that way through. So, and also I like to put the negative u to 1/2 together, so I'm not doing two things separately. I want to just do two things at once. Okay, so if I FOIL this out, 2 minus u squared is 2 minus u times 2 minus u, and this becomes 4 minus 4u plus u squared. Okay, any questions so far? Okay, what's our last step before we're ready for power rule? Distribute, right? Once you distribute through, then we're clean. Every term is nicely separated, no parentheses getting in the way. Then after that, we can do power rule. Okay, what's u to the 1/2 times u to the first power? Yep, 3/2. And then last one, u to the 1/2 times u to the 2 is, yeah, 5/2, right? 1/2 plus 4/2 is 5/2. Okay, so now we're ready, right? Power rule for each of the terms. Add 1 to the exponent divided by the new exponent. Right here.
Yeah.
Yeah, right. So you see how there was I replaced dx with -1 du. I just made the -1 and 1/2 go together, so that I don't have to distribute them separately. I just can just do it all at once I'm ready. Yeah. Okay, power rule. Okay, dividing by these messy fractions, the same thing as multiplying by the reciprocal. So dividing by 3/2, same thing as multiplying by, sorry, yeah, dividing by 3/2, same thing as multiplying by what? 2/3, right? So negative 8/3. And then the same thing as multiplying by 2/5, so 8/5. Then 2/7. Okay, we took the antiderivative. We basically have our answer, but is there anything else that needs to be done?
We're looking for you.
Okay, sorry, questioning?
So you went -4 to 1/2 to, you change it to 3/2.
Yeah. Because we're doing power rule, right? So we add 1 to the exponent. 1/2 plus 1 is 3/2. And same thing, 3/2 becomes 5/2, 5/2 becomes 7/2. Yeah.
So when you distribute the negative out, like, could you end your answer with just like a -c instead, or you have to distribute it?
So it's not wrong if you did -c, but -c is same thing as adding a negative number, right? Because constant plus c can represent any variety of positive and negative numbers. So we just typically just say plus c.
Just distribute.
Right, right. Yeah, so technically we are distributing that negative through, but a plus c can, because it can handle negative numbers as well, we just leave it as plus c. But if you did -c, technically that's not wrong either. Okay, anything else that needs to be done? Or is it the last thing? In terms of what? In terms of x, yeah, in terms of x. So, yeah, again, just want to point out that typically, if students have trouble with bringing back the x variable, it tends to be these types of problems. I think because we've done a substitution already, and it feels like, okay, I've already done a set of substitution. In this case, 2 sets of substitution. Why do we need to do another one? It's because we're still stuck in terms of u, so we got to bring back in terms of x. Right, so. Any questions? Okay, so page 9. We're going to still talk about U-substitution, but now with definite integrals. So that means that just means we have one additional step ahead of us. After you go through U-substitution, we're going to have to involve the bounds after the antiderivative. Okay, so all right, here's the next page. Okay, so anytime we see bounds in the problem, the first thing we do is we ignore it, right? We don't involve the bounds with the expression. We're just going to pretend like the bounds aren't there. And after we've taken care of this problem we see in front of us, then we can bring the bounds back and we can decide what to do with it. But it's never the first thing we do. It's the last thing that we do. Okay, so let's look at this 2x x squared minus 2q. I'm purposely removing the bounds so we can just focus the problem at hand here. Okay, let's go down our options, right? So expansion, power rule. Can we expand our way through this problem and expand and get it ready for power rule? I'm sorry? We could, but I mean, it's doable. But what's a little bit messy about this? Yeah, 3 times, which isn't too bad, right? But just to let you know, you're not, you know, in this course, you don't have to worry about expanding anything 3 times. 2 times, that's fair, but 3, we want to look for another option, right? So it's doable with power rule. It's not the worst thing, but what's our second option? U-substitution, okay. What could be our U value? Square minus 2. I'm always underlining the U value and the dx because we're going to make that make those two be replaced first. Do we see any potential issue, or will things work out? It should work out. Yeah, that x squared is favorable for that x, so we know that this is going to be potentially an easier version of than the one that we did before, right? There's not going to be potential that change of variable we got to worry about because the degrees are going to should work out each other. Okay, so let's start off there. U equals x squared minus 2. All right, derivative du dx, x squared becomes the -2 goes away, cross multiply. Dx equals All right, let's make our substitutions here. Everything that's not underlined, we want to make sure we keep them in the problem. Times 2x times. Okay. Times. Okay. All right, we can't move further until the x's cancel out. Or is that going to work? Oh, yeah. So, and the 2 goes along with it, so that's nice. There's not even any coefficients we got to keep track of. All right. Whenever you go through your substitution, you should be looking at an easier problem than we started with. And we are. That's good. What rule can we use for this? Our rule. Okay. U to the third becomes. Okay. Normally you would do a what? A plus. In this case, right, there's no plus c because we know there's bounds. That plus c will just go away. Okay. We have our answer. Well, before the bounds, but we started with which variable? X. So we got to bring that back, right? So if I want to bring that back, that's same thing as 1/4 times parentheses what? X squared minus 2 raised to the. Right, so this is what we would have done if we did not see the bounds at all, right? We would stop here and we would say plus c, and that would end the problem. But we have bounds involved, so there's one additional step. And the one additional step is having to worry about what to do with the bounds, because we know that this is now restricting or giving us boundaries. And so we know we're getting an answer that is area related. We know that we're going to get something that's a number rather than just variables. Okay, so we can place our upper and lower bound. And what do we involve first? The 2, upper bound first, okay? So sometimes this number may be smaller than this number. If it were, it's fine. You can still always plug in the top number first. You can change the order of the bounds, but if you did that, you got to pull a negative out in front. So I would say, if this number is smaller, just go ahead and go through the same process. Things will work out in the end. You don't have to worry about making the adjustment for it. Whatever number you get, that's still the answer. Okay, upper bound first. minus, right? Minus, then the lower bound gets involved. Okay, so 4 minus 2 is 2. 2 to the fourth is 16. I have 16 over 4 minus. 1 minus 2 is negative 1. Negative 1 to the fourth is 1. So minus 1/4. What's my answer? 15 over 4. Okay, I want to show you a second option of doing this problem. This option, I think ultimately is going to be the one that you prefer, which is fine. But I do need to show you the second option because sometimes the AP exam multiple choice can force you into this knowledge of this method. So you just have to kind of be aware. But if you're doing it by hand from beginning to end, this is the method that I think most students would prefer, which is fine. Now, what's different about the second method?
There's
Oh, sorry. We're sorry. We're still on example 1, but I want us to leave the space for us to go through. This is method 2 here of evaluating the bounds. Now, everything up to this point is going to stay the same. So I'm going to write that everything up to this point, u to the third du, right, is u to the fourth over 4. Okay, so this is where the path is going to diverge here. We're actually going to stop here and then evaluate the bounds at this stage rather than bringing this in terms of x. But what is wrong with using 1 and 2 at this stage? Yeah, good. The bounds are in terms of x, but the antiderivatives in terms of u. So there's a mismatch, right? So the idea is that we either have to get our antiderivative and the bounds in terms of x, or the second option is let the antiderivative and the bounds in terms of what? In terms of u. So that means we have to adjust the bounds. We got to convert the bounds in order for them to be usable. So instead of taking this to the x variable, we want to just instead move the bounds in terms of the u variable. So our two bounds are in terms of x is 1 and 2. So I'm going to say this: if x is 1, then u is, there's my conversion. My conversion is that x squared minus 2. So this is how I can convert from one variable to the next. So if x equals 1, then u is equal to x squared minus 2. And if I plug 1 in for x, what do I get? 1 minus 2 is negative 1. Okay. Okay, let's convert the other bounds. If x is equal to 2, which is my original x upper bound, then to get it in terms of u, x squared minus 2, u equals what? 4 minus 2 is 2. So instead of using 1 and 2, which are in terms of x, we're going to use negative 1 and 2, just because the lower bound variable got converted to a u variable. And then the upper bound variable got converted to the upper bound value. Okay, now what can we do? Yeah, up what number first? 2. Okay, so I get 2 to the fourth over 4 minus negative 1 to the fourth over 4. 2 to the fourth is 16. 1 to the fourth is 1/4. Yes, and we should, right? We should get the same answer. It's the same problem, we're just evaluating the bounds at a different spot. Right? Either do the bounds at the X level with the original bound, or you can do your evaluation at the U level, but then you gotta bring the bounds to the U variable as well.
So it's always gonna be like x squared minus 2.
It depends what the U value is. Right, but yeah, it's always going to be, the conversion is always gonna be whatever your U-substitution start
Okay.
point, and that's always gonna, this is the way that you're always gonna convert, depending on what the U value is. I think most students prefer this one. It just feels more natural, right? Because we're eventually gonna get to our X anyway, so if we think of it as tacking on the X, then I think that's fine. I think this is the way that most students prefer. But I will talk about some advantages of this method. The advantage of the second method is that when you're splitting up your evaluation at a different stage. So this is a little cleaner to work with than this. It's not a whole lot more, but you got x squared minus 2 to plug in. Here you have just u to the fourth, but you're splitting up the work with the converting of the bounds. So ultimately, if you already go through that work ahead of time, this is going to feel a little cleaner because it's just a little bit less to have to plug in all at once. You can kind of split up the workload between the bounds. But I understand if students feel more comfortable with this, then you can go with this. But the reason that I need to show this to you is because sometimes AP exam can work a problem to this stage, and then you have to figure out what is appropriate with the next step. Sometimes it just works the problem halfway, and it just wants you to know what's equivalent to it. So sometimes they're converting the bounds in terms of U instead of in terms of X. Okay. Now, having said that, there is one other method that we cannot do. And this is a trap that a lot of students fall into. They get to this stage, okay, and U to the fourth over 4, and they say, well, I basically have my answer. I'm just going to plug in the bounds as I see it. I know that you can't use the original bounds on because there's a mismatch. Now, I know that if you work it out this way, it's still going to end up giving you the same answer, but that's just more of a coincidence. Okay, so just make sure that if you got to pick one of the two. Either get your antiderivative in terms of X and use the original bounds, or leave it in terms of U, but then you got to convert the bounds. But we can't use X with U. We're not going to get, that's not going to work out. I know in this case it kind of does, but that's more of a coincidence. Okay, so there's only two methods. There's not that, but sometimes students choose a third method of mismatching, and that's where we run into the issue. Okay, so there's not much to this. It's just we got to make sure that either that we can follow through with the full steps with the bounds rather than mismatching. Okay. Okay, I'm going to skip example 2. This is change the variable with definite integrals. That's a little bit more than I feel like we need to do. So let me go to the last topic I need to go over with you, and that is with even and odd functions. Yes, in a way, but there's still a few more things, right? There's still, when we get to our review, there's still a little bit. But yeah, essentially this is it. I'll do the review at the end. Let me make sure that we can get through the even and odd. So this is page 10. Okay, so this is what even and odd tells us. Even and odd tells us that sometimes you have functions that behave a certain way in terms of visually. So in an even function, if a function is even, this is what could happen. A function even means that your graph is going to be symmetrical about the y-axis. Your y-axis kind of acts as a mirror. or what's happening to the left and to the right. So if I have a graph that looked like this, then my function is considered even because I can take my graph and fold it along that dotted line and everything matches up. So if I can visually convince myself that's going to happen, then I have an even function. So the rule says that even function means that I can take half, or I can take what is to the right or to the left of the axis, and I can double it. If I double that value, then that's the same thing as taking the integral or the area of the entire region, because I have mirror images. So if I just double half of it, then it's the same thing as doing the full region. Okay, so symmetrical by the y-axis. Now, odd function is equal but opposite. Equal area, but they're going to be opposite in terms of everything will cancel each other out. So in other words, let's say this was negative a and a. If I had a graph that looked like this, that's above the x-axis, then from negative a to a, I'm going to have what? A graph that's below, right? They're going to be equal area. So if I add up the region from negative a to a, as long as they're the same distance away from the y-axis, they're always going to zero out. Because if there's a negative 3 here, then there'll be a positive 3. If there's a negative 4 here, that's positive 4. That's the relationship for an odd. So if you know it's an even function, you know your graph will always be, not always going to look like this, but it will always be mirror images on both sides. And an odd function, it may not always look like this, but it's going to have that symmetrical but opposite. Anything, if I add up all the regions to the left and to the right, as long as I'm the same distance away from the origin, this should all zero out. All right, let me show you a few examples here. There's a certain order that I want you to do things, because if you don't do it in this order, I think it could throw you off. So I think if we just follow these very specific order for even and odd functions, you're not going to run into some, you won't, it'll be easier for you to avoid getting confused. So example 3, it says, suppose that g of x is even functions. Okay, so already know what we're expecting, right? We're expecting a mirror image on both sides. So however way we draw it on one side, ultimately at the end, we can take a step back and convince ourselves, okay, I can fold my graph along the y-axis. I convince myself everything will just line up perfectly. Okay, so we have 2 integrals here, integral from 0 to 3, integral from -4 to -3. Okay, we're going to use these 2 properties to help draw our graph. And then in the end, we're going to add up the parts that they want us to add up. Okay, so the first thing I wanted you to do is identify the interval. Don't look at the area. Identify the interval that has a shorter region, shorter span, shorter width. Which one is the shorter interval here? I would say -4, -3, right? That's only in a width of 1. This is a width of 3. I know the area is less here than here, but you want to start with a shorter interval. So that's the first thing I want you to do. You want to graph your shorter interval first. Shorter or your smaller interval first. Okay, so let's. Okay, so from -4 to -3, I'm just going to freehand draw this here. -4 to -3. Okay, +4, above or below the x-axis? Above. So I'm just going to draw a mound here and call it 4. Okay, good so far? Now, before you draw the second interval here, I know right now it doesn't feel like a big deal because we're not seeing the full extent of some more difficult problems. But I think this will always help us keep things in order. The second thing I want you to do is go ahead and fill out the other side. Okay, before you do the larger interval, fill out the other side with what you know. Okay, so we have the left side here. Is there anything that we can do on the right side? We know it's an even function. So if there's a region from -4 to -3 with a positive region of 4, what can we do on the other side? Yeah, from 3 to 4, we can do the exact same thing, right? We don't know exactly what's happening to the left and to the right of it, but if we're going to create a mirror image, it's gotta be the same thing, right? Are we good here? Now you can fill out the last. Now you can do your large interval, graph your larger interval. Okay, so from 0 to 3, 0 to 3 is what? Above, so right up 2, so above the x-axis. And then, and if this is true, then can I fill out the other side? Also what? Yeah, -3 to 0 is going to be also 2. Now, this order doesn't feel like a big deal because we could have done it out of order and it still would have worked out. But when things begin to overlap with each other, then having these set in stone is going to be a lot better for you to anchor the information on your graph. Okay. All right, so do we have mirror images on both sides of the y-axis? As best we can, we do, right? Okay. So now we're going to total the area. It may not be the full area. It's just going to be whatever they're asking for. So from -4 to 3, we're going to just total those numbers up. So from -4 to 3. What's that equal to? 4 plus 2 plus 2 equals 8. Yep, that's your answer there. All right, good so far. All right, example 4. Same as example 3 in terms of the properties given, but now we're going to make it an odd function. Odd function. So, okay, where do we start? Good. Don't look at the area, look at the width. Shorter width is going to be where you want to start. Okay. Okay, what's our next step? Fill out the other side, fill out the opposite side. So if we know this side is 4, what do you know about the other side? Because odd, so we're going to get equal but opposite, okay? All right, so now let's do the larger interval. Larger interval is from 0 to 3. 0 to 3 is a positive 2. What can we say? What can we do to fill out the rest of this graph? What can we do from -3 to 0? Therefore, yeah, opposite of 2 is -2, right? So if we want to double check our answer, our graph, we should be able to add up all the numbers and it should total what? 0, and it does, right? Now 0 is not always the answer because the interval may not give you the same distance from both sides of the y-axis. So this one is only asking you to add from -4 to 3. And what do we get? Questions so far? Okay, so I think example 5 is where we're really going to need to follow this order. Otherwise, it's going to be really, really hard to see things clearly. So example 5. Okay, so we're back to an even function. Okay, so it says if 3 to 6 is equal to 7 and -6 to 3 is 12, find the integral from 0 to 6. So first things first, look at your width. Where do we start? That's the shorter interval, right? Okay. All right, what's next? Yeah, fill out the other side. Do not do the larger interval until you get that other side filled out, okay? Good, so from -6 to -3, what can we say? Also what? Also 7. Okay, so this is something that we haven't seen yet. It says the integral from -6 to 3 is 12. So -6 to 3, that's spanning across a region that we already have information about, right? So -6 all the way to 3 is equal to 12. Okay. Now, what you don't want to do is this. If you did this whole thing is 12, then it starts to make things confusing. It's already 7 here, and you want to add 12 to it. It just feels like that, we already have this set in stone. We don't want to create a region that is overlapping, right? But what we do know is that when we add everything up, it should equal to 12. So this is already done. We don't want to step on this region here. But we do know that when everything is said and done, this should add up to be 12. So if this is 7, then what remains from the rest of the interval? 5, right? So I know I can do 5. That is spanning across both sides. But it's still an even function. So what can we say on either? Is there a way to split that 5 up? Yeah, exactly 2.5, right? So the most common mistake that I see students do is they start overlapping the region with 12 and 7, and it just makes it hard to know what's going on. So when there's an overlap, you can put up to the side that, okay, I know that means I have something that I know and something that I don't know that's going to add up to be 12. And then from there, you can decide how you want to split that up. Okay, so we start with the shorter interval, we filled out the other side, and we gathered information about the larger interval, and then we filled out accordingly. So now from 0 to 6, what's that equal to? 9.5. Okay, we'll practice more with this. This is definitely a test topic, but as long as we don't try to overlap things when they're not supposed to, I think we should be, that'll really help you organize your picture. All right, check your calendar for your homework. Come get your phones. We'll start test review tomorrow. Our test non-calculator is Friday. Oh, I will have your quiz grades in the grade book by today, and I will give you your quizzes back tomorrow.